me.
No, it's genetics.
I think it bothers us. I really can't. Come on.
I would have heard about it.
Like, if I'm really good at wrong with exams, he's like, "Oh, should I go?"
Okay.
It's my fault, but you're still gonna point left.
Okay, so I just want to go through where we ended on Monday in terms of the Gabriel synthesis. So we're going to talk about a number of methods that can be used to make primary amines. And so the classical one was to take succinimide and react it with a base to deprotonate the nitrogen off of the succinimide to make succinimide anion. And so the succinimide anion then can be used to react with usually a primary halide. I don't know how well secondary will work, so we usually just stick to primary halides. So this N- is going to come in, kick off the chlorine. We're going to do an SN2 reaction, and the net result is we're going to alkylate that nitrogen to form that compound. So then, in terms of this amide, we're going to talk more about this in the coming, I don't know, few weeks. That, remember, I've talked a little bit about the fact that when you have the Y group attached to the carbonyl, that can make, if it's not H and it's not R, then it's either a carboxylic acid or it's a carboxylic acid derivative. So that Y group could be an OH, it could be a Cl, it could be an O, C double bond R, so that'd be part of an anhydride. It could be an ester, or it could be the amide. All of those are either carboxylic acids or a derivative. And what defines the definition of a carboxylic acid derivative is something that when you react it with either hydroxide or acid and water, you undergo what's called a hydrolysis reaction. And that hydrolysis reaction then forms your carboxylic acid. Depending on whether it's an acid or base, if it's an acid, it'll form the carboxylic acid. If it's in base, it's going to form the carboxylate, and then it frees up the Y group. And so in this case, what we're going to do is we're going to treat this with probably hydroxide would be the best choice. So treat it with hydroxide and water. That's going to cleave those bonds around the nitrogen. I'm not as much interested in the dicarboxylic acid here as much as I'm interested in freeing up the primary amine that I just made. And so that is classically what we call the Gabriel synthesis. And so it's a classical way of making a primary amine. Because if you try to make a secondary or a tertiary amine, isn't going to work because your requirement is that SN2 reaction to start with. So that's kind of where we ended, and since my computer ate both the video from, well, it didn't eat, it ate up until it died on Monday, but it did eat the 8 o'clock in the morning video. So I'm just going back so it's there. So that's one way to prepare a primary amine. Another way to prepare a primary amine is to use another compound, two compounds, which are going to be called azides, and we'll use a C triple bond N. So there is, if you're looking for like a seamless flow between reactions and amides, you're not going to find it. It's just like a mess of different reactions that we kind of put together. So for the azides, what I'm going to do is I'm going to take an alkyl halide, and I'll basically use a primary one, and I'm going to react that with something like sodium azide. So what's an azide anion look like? It's got 3 nitrogens double bonded together, with the outer nitrogens having 2 lone pairs. Overall, it's a -1 charge. So if I determine the formal charges on this, there would be a plus charge on the middle nitrogen, -1 on either side. So overall, it's a -1 charge. And so that azide then will come in and do an SN2 reaction on a primary halide, so that now it'll substitute for the chlorine, and what I will end up doing is one of the lone pairs on one of the nitrogens that's negatively charged is going to attach to the carbon, and then the other 2 nitrogens get a positive and negative charge, so that overall we've got a neutral molecule. Now you may say, well, where's the amine going to come from? What I'm going to do is I'm going to write the resonance structure for this that's going to turn these final 2 nitrogens into a nitrogen gas molecule waiting to leave. So what I'd like to do is I'd like to make that N a triple bond. Now, there's a couple ways to do that. One wrong, one right. So if we think about how we're going to do that, the incorrect way of doing it is to try and move this nitrogen or that pair of electrons over there, because if I do that, the N nitrogen gets 5 bonds, which violates the octet rule. So I shouldn't do that. The other way is to take this pair of electrons, move it there. If I stop, the middle nitrogen has 5 bonds, violates the octet rule. So instead what I'm going to do is then move that pair of electrons to the nitrogen. So again, this is just the resonance structure. But what I'm doing is I'm setting up a leaving group. So that nitrogen kind of looks bad because it's got 2 lone pairs. But if I'm putting in my formal charges, that nitrogen has 1, 2, 3, 4, 5, 6 electrons it owns. It came with 5, so it's -1. The center nitrogen is still +1. And now the N nitrogen is 0 in terms of their formal charges. But what I've done here is now this is going to be N2, which will act as a leaving group. But what's my goal? Because I need to take a step back and remember, what am I trying to make? I'm trying to make an amine. So that means I'm going to have to displace that N2 group. What would be the best nucleophile to do that in order to turn this N into a primary amine? I need a nucleophile. I need something minus. No, because I don't want an OH minus attached to my nitrogen. What do I want? Just an H. So let's try H minus. So if I have an H minus, it'll come in. It will add to that nitrogen. and then I'll lose N2 gas, and at least I'll have one hydrogen attached to the nitrogen. And that nitrogen will still have 1, 2, 3, 2, 4, 6, 8. Still got 8. 1, 2, 3, 4, 5, 6. So it's still minus 1. And then with my N minus, if I go ahead and eventually add water to this, that N minus is just simply going to deprotonate. So that now I'm going to end up with my primary amine. So I'll use H minus here as the nucleophile. Then my question is, where does the H minus come from? No. Lithium aluminum hydride, or either lithium aluminum hydride or sodium borohydride. Which one's stronger? The lithium aluminum hydride stronger? Are we sure about that? So I would go ahead and use the stronger. I would go ahead and use lithium aluminum hydride for that. So again, another way to make a primary amine using azide. I would, once I make this molecule with the nitrogen leaving group in place, I probably wouldn't want to let it sit around too much, or else it'll probably decide to explode because of the nitrogen gas molecule in it. So I'd want to make it, use it, and move on. Okay. So that's with what's called an azide. So this is an azide. Another method that we can use to make a primary amine is to use lithium aluminum hydride with a nitrile, a C triple bond N. Mechanism here is going to be slightly different. So if I take this nitrile, and what we're going to find with nitriles is they are also carboxylic acid derivatives, so that when we react them with H plus H2O, we make carboxylic acids. We saw that with cyanohydrin. We hydrolyzed it to form the carboxylic acid. In this case, what I'm going to do is I'm going to react this with H minus of lithium aluminum hydride. And so what is the hydrogen going to attack? Which atom, the C or the N? You got two choices, the C or the N. Take a guess. C? Probably a good guess. So the H minus is going to come in and attack the carbonyl, and the pair of electrons is going to go to the nitrogen. So then the nitrogen is going to be negatively charged. The C triple bond N is just like C double bond O. And we're going to do a lot of these reactions. So let's see, in the morning class I sort of messed this up, but then I kind of fibbed to them a little bit on how the second step worked. And it's not like anybody called me on it. But the fun part of this, sort of, is that what's actually going to happen here is that, well, here's what I said happened. Oh, we'll just dump some water in here. We'll just dump some acid and water in here. And what'll happen? I'll make that. Right, because N minus is going to pick up the proton from the acid. And then I said, well, what is that called? I had exactly the same response this morning, too. It starts with an I. It's an imine. Then my next question was, are imines stable? No. What happens when they react with acid and water? How did I make an imine? Yeah. It is. This has a mind of its own. That's how we made it like a month ago. Wasn't it just like last week? I don't think it was Monday, but I think it was last week. Oh yeah, it was Monday, wasn't it? Because we did reductive amination. So what I said was, oh, well, if we hold on to this imine, if we can somehow just add a little bit of acid or water or something here, if we hold on to this, then what we could do is react it with hydrogen and palladium, and we could do a reductive amination down to the primary amine. If we don't, if we use excess water and acid, then the imine will end up forming the ketone. So one of the things that we're going to find later on is if I don't use H minus, but if I use like an R minus group from a Grignard or an organolithium, I'm going to be able to take a nitrile and make a ketone out of it by adding a second group. But in this case, we will just assume that you can take this imine and kind of make it and then do a reductive amination down to the primary amine, like we did on Monday. Now, the reality is that the lithium aluminum hydride completely reduces this down to a primary amine. But I'm going to have to hold up on that step because it involves a little bit of, it's not magic, but it's a different way of looking at the molecule. And so we'll just stop here. And it ties in with Monday. Okay. So that's one of the ways we can reduce the nitrile down to a primary amine. And like I said, later, what we're going to do is we're going to end up either adding an H minus or a C minus and converting this either to a ketone, or actually we can also convert it to an aldehyde. We just need a slightly different reagent. So what's my point? I should probably think about that for a minute. My point is that we're going to actually do some of these reactions where we add Grignards and H minuses to molecules and make imines and hydrates and acetals. And then we have to remember that those compounds are unstable and reverse themselves down to aldehydes and ketones. That's actually why we talked about them before we get to a whole series of organometallic reagents. So that's nitriles and the reduction of nitrile. Okay. All right, so we can make primary amines from Gabriel synthesis, from azides, and also from nitriles. What else can we do now with amines? Because now we're going to move away from synthesis of amines to the actual reactions of amines. So the next reaction of an amine that we're going to do is we're going to react it with an aromatic heterocycle. So here we have pyridine, and we know that that's aromatic. And my question is, if I add an electrophile to that pyridine, where's the electrophile going to go? Is it going to add to carbon A? Is it going to add to carbon B? Or is it going to add to carbon C? Okay, nobody knows. Was it just going to be a guess?
Yeah.
Okay. So nobody knows except a guess. So here's what. How do we figure that out? By the way. Well, okay. So do what? Add the E plus to carbon A and write all the resonance structures. And add E plus to carbon B and write all its resonance structures. And add the E plus to carbon C and write all of its resonance structures. And so how do we know where the E will ultimately add up? The one with the most resonance structures, or the combination of the most stable resonance structures. So I could do that with this molecule to figure out what the combination of resonance structures is and where E plus should add. Should it add to A or B or C? And then we could take our molecule pyridine, or sorry, that was pyridine. This is pyrrole, which is also aromatic since the lone pair is part of the nitrogen lone pair is part of the system. And I only have 2 carbons to choose from this time. So I could add my E plus and I could say, okay, where should E plus add, A or B? Anybody know the answer to that? Nope. So we got to do the same thing. So I mean, I could do this for you. That doesn't seem... I already got my grade in organic chemistry. So I think this would make a good take-home quiz problem. Sorry, problems, period, or plural. So what are you going to do? You're going to add the E plus to carbon A and write all the resonance structures. Put it on B. I mean, this is very similar to When's the last time we had to do this? The exam. Yes. That was one of the questions on the exam. So add the E plus and then write the resonance structures. Now again, is it the most number of resonance structures, or could there be a combination that's more stable? We'll have to find out. But if we do that, then that's going to tell us where to add the E plus. Okay, because heterocycles, with putting the nitrogen in the ring, that's going to change the reactivity. There's no more orthopara, but there are positions next to the nitrogen. So there's your take-home quiz problem. And who knows, maybe they do that in the top hat book, I'm not sure. Well, maybe they do. Okay, so we want to do this so we can practice writing it and go back, and we probably need more practice on that anyway. Okay, so that's a reaction of that's a reaction of an amine that's part of a heterocycle. Great. Now, some of the more important reactions of nitrogens, of amines, are elimination reactions, and there are 2 eliminations. Now, to set this up, let's say that I was to react that molecule, that alkyl halide, with a base. I could get 2 possible alkenes out of it. A and B. What base would I use to make A? Josh? I would use tertiary butoxide to make A. Do we agree with that? Then what do I use to make B? H2 minus. This has nothing to do with amines. Hold on. It will. What do we call product B? The most stable alkene. It's called the blank product. No. I'm hearing it. You're just not. Be aggressive with your answers. What? Zaitsev product. No, you can spell it. You can spell it like with Z's or S's or.
It's named after a guy.
Yes. Yeah, but I don't think it's this one. We'll just erase that. It's Zaitsev, who was a Russian chemist. But again, the difficulty is he was a Russian chemist. It got translated to German, so spellings are all over the place. So Zaitsev, yes. Zaitsev found that and Zaitsev did his original eliminations with alcohols with like sulfuric acid and heat. And he found that he always got the major product being the most substituted alkane. Now, take a step back into perspective. Given you've learned about spectroscopy in the lab, right? And how difficult it is to determine the structures of molecules if you have a $250,000 NMR and a $50,000 IR and maybe another $100,000 mass spec. Zaitsev had nothing. He had no instrumentation at all to come up with that rule. So determining the structure of maybe a couple molecules might have been like a year or a career's worth of work. So they did all of this work pre-instrumentation, which, again, in perspective is like, okay, every organic student from here to eternity should have to learn his name, because what he accomplished. So that's enough about Satan. What's the other one called? It's the Hoffman product. And I don't normally, I'll give it, but I won't harp on it. Like, oh, this is the Hoffman product. And if I do, I'll say, well, the Hoffman product comes from the Hoffman Elimination Reaction, which we'll talk about second semester, which is today. So Hoffman elimination gives you the least substituted, least stable alkene. There's no sense in talking about it in the first semester, because now's the time we're going to talk about Hoffman elimination. Obviously, the mechanism is different. And so here's what happens with Hoffman elimination. I'm going to take a molecule, and I'm going to just kind of skip ahead here. So I'm going to take a primary amine, and what I would like to do is I would like to exhaustively methylate this amine. What does that mean? That means the net result is I'm going to use 3 equivalents of methyl iodide in a basic reagent. Because as we learned on Monday again, that the nitrogen will come in and react with the first equivalent of methyl iodide, and we will add our methyl to the nitrogen, but those nitrogens like to remain protonated, so we'll end up with, there'll be still 2 hydrogens there, and then the I- is going to end up as a counterion. So this is always what happens when we alkylate an amine, is we always end up with ammonium salt. And the ammonium salt means there's an ammonium, and then whatever halogen we kicked off hangs around as the salt. Then we have to treat this with a base in order to remove that hydrogen from the nitrogen, so that now I end up with an NH with a CH3, the so-called free amine. So when we talk about alkylation, we have to do this stepwise. Alkylate, use base to make the free amine. Alkylate the free amine, use base to make the next free amine. So when you exhaustively alkylate it, it means I'm going to put the maximum number of alkyl groups on the nitrogen, which is 3. So now I've exhaustively alkylated it, so I've got 3 methyl groups on the nitrogen, so it's an N+. And what am I going to do here? I've written it up. I'm going to add an extra methyl group in here. So in Hoffman elimination, I've just turned that nitrogen into a leaving group. So that now when I treat this with heat, there's my leaving group, the nitrogen, so there's the alpha carbon, there's a beta carbon, there's a beta carbon. Do those beta carbons have hydrogens? Yes, there's a beta hydrogen, and over here there is 1, 2, 3. beta hydrogens. So I have two possible products. So there's my two possible products. And so which one of those am I going to get? This one? Why? No. It's the Hoffman product. And the Hoffman product is always the less stable product. This morning I made a big deal about the fact that the Hoffman product is always the least stable product. Then I went through this and then said, what's the major product going to be? And everybody looked at me. Then finally somebody said, oh, it's that one. And I said, why? Because you just said that like 5 minutes ago. So yeah, that's because it's the Hoffman product. Now, the question is the mechanism, right? What's the mechanism of this? Is it steric hindrance? Is it... So here's the critical thing. There's no base. Right? When we make the Hoffman product doing E2 with tertiary butoxide, it's a question of steric hindrance. The base comes in and grabs one of these three hydrogens because there's less steric hindrance there. But when you do Hoffman elimination, there's no base. It's heat. This reaction is driven by heat. This nitrogen group, you'd think, oh, well, it's just fly off of the carbon. It doesn't. It takes heat to get rid of it. So that changes the mechanism so that there's one criteria that we use to predict the major product. And that's this. Whatever beta hydrogen I lose, this is still an E2 mechanism. So what does that mean for the geometry of the transition state? It has to be anti-periplanar. Right? It's got to be anti-periplanar. So the beta hydrogen and the leaving group have to be anti-periplanar. Now, and this I don't quite know. This is always something that's hard to explain. But when the base is involved, or when there's a carbocation involved, the base takes an active role. It comes in and rips the beta hydrogen off. But there's no base. So this is kind of a thermally driven process. The question becomes, how many hydrogens can achieve the anti-periplanar geometry on each one of the beta carbons? And the carbon that has the most hydrogens that can achieve that, that's how the reaction is going to occur, or where it's going to occur. So in this case, I have 3 beta hydrogens, each of which could be rotated to become anti-periplanar to the leaving group. Over here, I just have 1. So when you're doing this process thermally, it depends on the number of hydrogens that can become anti-periplanar. And what we've got here is we've got 3 versus just 1 there. Now I can restate that a little bit differently, but not much, to say how many different conformations are there here that lead to the hydrogen and the nitrogen being lost? 3. How many conformations over here are there? Just 1. So when you take a look at that, the 3 to 1, where there's only 1 conformation, even though I'm applying heat, I've got to get the molecule to go into that correct conformation, and then it'll lose the hydrogen and nitrogen. Whereas on this side, it's already there, or it's pretty close to being already there. So the thermal idea of heating this up changes the mechanism. So our criteria, because this class has all been about the rules, right? You can't write the major product unless you know the rules. Okay, the rules are constantly changing. Depending on the molecule, you're that, but that's just the way it is. So in this case with Hofmann elimination, it's based on the number of beta hydrogens you can lose. Because in general, that gives you more conformations. And again, because there's no base, and that nitrogen's not going anywhere until it's heated, so that the hydrogen and the nitrogen get lost. Okay. Now, on Friday, what we'll do is, so we know we get the major product that's least substituted, but we need to make this more interesting. And the more interesting part is, what if I gave you a molecule that has some stereochemistry to it? So that you're going to have to take a beta hydrogen and you're going to have to rotate it to figure out whether you get the E or the Z isomer. So we'll talk about that on Friday. No. I had 7 minutes. They would fire me if I stopped now. Yeah, they can't fire me. It sounded good. They would shame me. No, I'm just a lowly. Well, I can judge others, but everybody's always judging each other. So. Okay, so there is another elimination that goes with this. So this is the only kind of things that tie together, although actually that's not true. This isn't a series of random reactions, because we talked about alkylating on Monday and the fact that you had to use the base to deprotonate it. And we did talk about reductive amination, which I used earlier. So there are things that go together. There is a second elimination that will also give you the least substituted product, but instead of the hydrogen, the beta hydrogen and the leaving group being anti-periplanar, they have to be coplanar, meaning in the same plane. So that this is sort of the yin of the yang of the stereochemistry. So if you can form one easy isomer with one reaction, you can form the other easy isomer using the other reaction. And so this is Hofmann elimination. The next one is called Kok Elimination. And for Kok elimination, let me start with my same molecule. I'll start with my primary amine in this case. And now I'm just going to add 2 alkyl groups to it. So I'm going to add 2 CH3s, 2 CH3Is, along with the basic conditions, so that what I'm going to do is I'm going to end up putting 2 methyl groups on the nitrogen. So I'm going to make a dimethylamine. And now what I'm going to do is I'm going to oxidize it. And I'm going to oxidize it by treating it with an oxidizing reagent, something like peroxy acid works well. Hydrogen peroxide might work well as well. So there's a lot of different amine sort of functional groups. There's primary, secondary amines, but then if I oxidize that nitrogen, what I end up doing is putting an O onto that nitrogen, and the O has a negative charge, while the nitrogen then will have the 2 methyl groups, the O, and a positive charge. And this is called an amine oxide. You know, all the different nitrogen functional groups, when you've got enamines and imines and Schiff bases, this is an amine oxide. Well, then we had the oximes and the hydrazines and the hydrazones and all of that stuff. Amine oxide. It took me 5 minutes to remember it this morning, but it finally came back. Which isn't bad, because I'm losing it, but I'm not quite there yet. So this is an amine oxide. Now, what the amine oxide is going to do is it has enough space where it's going to come and it's going to grab the beta hydrogen. And it's going to grab the beta hydrogen that is most sterically accessible. So in other words, least sterically hindered. Well, what it's going to do is it's going to form a 5-membered ring transition state. So that as the O- grabs the hydrogen, the pair of electrons goes to form the double bond, and then the pair of electrons goes into the nitrogen. So again, I'm going to form a 5-membered ring transition state. This isn't our first 5-membered ring transition state, but hopefully what you remember about the 5-membered ring transition states are that they can't wrap around and be on both sides of a single bond. In other words, they can't be cis and trans. They have no choice but to be cis. In this case, this hydrogen has to be periplanar. And all that means is it just has to be planar to the NO group. But it's not anti. Because the 5-membered ring can't stretch that far. And so now what I've done is I've set up the reaction to give me the least substituted double bond, but now from the periplanar geometry. So if I went back and I gave you that same molecule, because the leaving group and the beta hydrogen are going to be periplanar and not anti-periplanar, I'm going to get the opposite stereochemistry. Whether it was E or Z or cis or trans, I'm going to get the opposite one. And so on Friday, what we're going to have to do is we're going to have to manipulate these two using our sawhorse projections. And we're going to have to rotate to make things anti-periplanar, and we're going to have to rotate to make them periplanar, so that we know what groups are going to be cis and what groups are going to be trans when we do the reaction. So this is Kok elimination. Josh? Doesn't it give you the most stable? No, it doesn't, because again, what this is doing is this is grabbing the least hindered. This is grabbing the least hindered of the hydrogens. And if you're thinking cis or trans, whether it's most stable, once the stereochemistry is fixed, that hydrogen's got to rotate up and become periplanar. So we'll see both examples on Friday.
The reason why I asked is because of the Hoffman product that we were looking at before, it created only a single substituted, where here it's a tri-substituted.
Well, what I haven't done here, yeah. Yeah. So what he's pointing out is that I'm taking away the most substituted hydrogen. It should be the exact opposite. So I will redo this slide correctly. And I always put the slides in and the video in so you can go back and, I suppose, print them out if nothing else. But I will redo that over here when I put it up on you're exactly right. That's a good catch. It's supposed to grab that one. It's supposed to grab the least substitute one.
Was it just like a mental thing with oxygen?
It's always a mental thing. There's no hot mess going on, just a mess. Okay, for Friday, the take-home quiz problems I just gave you, I will probably write that up and put it in Canvas, but you can start now. I'll redo this. Remember chapter 20-something, ketone aldehyde, top hats are due on Monday.
I just had a question about lab tomorrow, if you needed me there any earlier.
Any earlier, because I'm
doing the